So we're going to start sketching some lines, and I think the thing that people have the most trouble with when sketching is the word sketch usually means art. It means uh, sketch a landscape or do a sketch of your sister or whatever. And when you do a sketch in math, it doesn't look like a picture. It looks like a line or a bunch of dots. It's not really art. I suppose we could argue that, but anyway, I digress. Um, when you're doing a sketch in math, it's actually asking you to find all the places on a Cartesian plane. So let me write that out for you. Find all the places on a Cartesian plane where dot dot dot. Now this is the part where the specific equation comes in. So this word sketch in math is interpreted as this sentence. Find all the places on a Cartesian plane where. You need to use all the words when you write out a sentence. Pro tip. So in this particular example, it says, find all the places on a Cartesian plane where the y value is 4. Now that's not terribly complicated. I'm just going to quick draw a little grid here for you. So Cartesian plane has a y-axis, it has an x-axis, and it's got some ticks. 1, 2, 3, 4, 5. 2, 3, 4, 5. Okay, so I want to find all the places where the y value is 4. So this is the y-axis here. So I'm just going to count up to it. 1, 2, 3, 4. That place has a coordinate of 4 in the y direction. Now, that's not the only place. That's the place where the y is 4 and the x is 0. Well, the x can be anything. So let's pick a new x. Let's try 3. So this is where x is 3. I'm supposed to find where y is 4. Well, that's just here. It has nothing to do with the x. You notice there is no x in this equation. So find another spot. Is the y value 4 here? It is. Is the y value 4 here? Sure is. Is it 4 between these two places? Yep. How about between these two? How about between these two? And I don't know if you sort of see what's happening here, is that all of the places where y is 4 happen to line up in a nice straight line. So when you are asked to find all of the places on a Cartesian plane where the y value is a particular number, you end up with a whole bunch of places because there are lots of them. And they'll all line up just like so in a nice horizontal pattern. If I want to make this just a touch more complicated, like this, I've changed my sentence. I haven't changed the front part. It still says, find all the places on a Cartesian plane where the y value is 4. Subtract whatever the x is. So we're going to pick a place, like here. Right here, the x value is 0. So I've still got this line across here, because that's where y is 4. At this particular place, I have to subtract the x value, which is nothing. So if you don't subtract anything, then you stay right there. If I am at this place, the x value is 1. So I have to fall one square from this y equals 4 line. If I'm at x equals 2, I have to fall 2 squares from there. If I'm at x equals 3, I have to fall 3 squares from there. If I'm at x equals 4, I have to fall 4 squares from there, etc., etc. And if you see, I'm starting to get a nice straight line forming again. Now I'm going to erase this, and I'm going to pull up a grid that has, you can actually see the grid lines, so you maybe see a bit better. And then we'll try doing a few of these that have different numbers to start, and maybe put some numbers in front of the x. So we're going to make a sketch of y equals 5 minus 2x this time. Now, the language hasn't changed just because there's a number there. This word still means find all of the places on a Cartesian plane where the y values match 5 minus twice the x. So I'm going to find these places first. I'm going to find all the spots where y is 5. So I go to my origin and I count up on the y-axis, 1, 2, 3, 4, 5. So those places are here. Okay, that's where y is 5. So my second condition there is from this line, this place where y is 5, I have to drop 2 for every step I take in x. So here, my x value is 0. So I have taken no steps in the x direction. So I don't have to go anywhere from that point. But if I go to 1, once I make this a 1, I have to drop 2 times 1, which is 2 squares. So I drop 2. If I take another step, I'm going to have to drop another 2 squares. If I take another step, I'm going to have to drop another 2 squares, all from this line. Now, if you want to do a little bit of calculating here, this particular dot happens when x is 3. So if I tried that, put the 3 in there, 2 times 3 is 6, and 5 minus 6 is negative 1. So when x is 3, that's along this line, I'd have to start at 5, drop 6, and that would land me at negative 1, which is where I've ended up here, 1 below. Take another step in x, I'm down another 2. Take another step in x, I'm down another 2, etc. It looks like this line goes on forever, like so. Now, in the last example, I only went this way, but lines can go that way as well. So if I start tracking back that way, I have to undo that drop by 2. And if you undo a drop, that means you're rising. So continuing this line onward, you end up here, 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 off you go. And just as a rule in math, it's polite to always try and fill the grid that you've been given when you're trying to draw a function. You don't just stop someplace random because you want to be able to see how the pattern behaves everywhere. That maybe doesn't make a lot of sense when you're in grade 10 or grade 9, but when you get to grade 11 and grade 12, when this is more complicated, you want to see how the function is behaving all over the place. So just to recap, when I was asked to sketch this thing here, I was asked to find all of the places on a Cartesian grid where the y value is 5 less 2 for every x. I made a line like this. I'm going to clear this off, and I'm going to try another one. This time, instead of a subtract here, I'm going to put in an add. So I have a new line to sketch here. So find all of the places on a Cartesian plane where the y values are negative 7 plus 3 for every step in x. So again, I'm going to find that -7 first. So from my origin, I'm going to drop 7 on the y-axis. 1, 2, 3, 4, 5, 6, 7. That is where y is -7. Now, in this particular equation, from that line, I'm supposed to add 3 for every x I take. So from here, no x's, I go up none. 1x, I go up 3. 2 x's, I go up 6, because 2 3's is 6. 3 x's, I go up 9. 4 x's, I go up 12, etc. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yep, that's in the right spot. So you can think about it as all of the multiples of 3, right? 0, 3, 6, 9, 12, 15, 18, 21, 24. I'm just counting by 3's and counting them up from this number. Or you can go from each dot to each dot and just add an extra 3 each time, which, if you think about it, that's what you're doing when you're counting by 3. You're just skipping some numbers in between. So again, in the spirit of filling up the grid, I didn't quite make it all the way. So there I go. I'm all the way off that way. And if I continue this pattern, the next one is going to have to be there. And I can connect all of these in a straight line. Now, you, of course, being far more technologically advanced than I am, are going to use a ruler to do this. But I think my brain would explode if I tried to combine the clear screen, the acetate, and the computer all at once. So if you can kindly use a ruler or a straight edge, you will get nice clean lines, and I will just try and eyeball them as best I can. Where the y values are -2 plus 3/5 of a step for every x. Now that fraction is going to make things a little more tricky, but we can still start with this, right? Find the place where the y values are -2. So from the origin down 2 in the y direction, that's here. Now you're going to get a freebie at this spot, right? Because the x value is 0. So I don't have to add any of these on that spot. So I'm just going to fill that in. Now, if I were to take one step over, I have to add 3/5 to this line. So when the x is 1, I have to go up 3/5. That's going to be gross. I'm not going to be able to find 3/5 of this line. It's just going to be a guess. So instead of working hard or working messy, I'm going to let this pattern play out a little bit. Because when x is 2, I have to add another 3/5. That makes 6/5. Now that's still horrible. I don't know what 6/5 is. If I take 3 steps, I need another 3/5. That means I'm at 9/5. Still don't know that. 4 steps in x, I need another 3/5. That's 12/5. That division still doesn't go evenly. But if I take 5 steps and take another 3/5 here, I'm at 15/5. Now that fraction there, or forgive me, there are no such thing as fractions. There's just divisions that we can't do cleanly. 15 divided by 5 is 3. So that's going to happen again, right? Every 5 steps, I'm going to end up with 3 squares being added up. Now I can count that cleanly. So from here, if I just skip this dot, because I don't know exactly where it is, right? It's got to be there. And I skip this dot because it's not clean. And I skip this dot because it's not clean. And I skip this dot because it's not clean. When I finally get to x is 5, I can go up 3 full squares. And I know that it's boom, right there on the grid, because after this many pieces, these little fractions of squares, finally, they eventually add up to a certain number of full squares, and I can just dash it in there. Now that's going to happen again. Every 5 squares, 1, 2, 3, 4, 5, I'm going to need 3 more full blocks added to this pattern. If I go back the other way, right, 5 more blocks, 1, 2, 3, 4, 5, I should be 3 lower. 5 more blocks, 1, 2, 3, 4, 5, I should be 1, 2, 3 lower, and they will nicely line up for you. So when you're looking at this, if you see a fraction, it's got a 5 in the bottom. So notice that 1 doesn't divide evenly by 5, neither does 2 or 3 or 4, but 5 does. If you ask yourself, what is the next x value that will divide cleanly by 5? So 1 times 5 is 5, 2 times 5 is 10. So I should be able to get a clean dot when I make x 10. Because 10 divided by 5 would be 2, 2 times 3 is 6, add 6 to -2, I should end up at 4. Maybe we'll rewind that and watch that again. But if I do that, 10 and 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. My y value is 1, 2, 3, 4, exactly where it should be. So you don't need to do all of this adding. You can just use the step pattern. It seems to be up 3 over 5, right? Up, positive means up, 3. It's literally over a 5. So from each place, up 3 over 5, up 3 over 5, and that will give you the pattern. And by connecting those dots with this line, you've actually included all these places accidentally. You didn't do it on purpose, right? You just said, it's got to go through the grid in these spots. But you were asked to find every single place on the Cartesian plane where this is true. And as soon as you struck in the line, you not only included the places where it works out cleanly, you also included all these heinous fraction spots. And all the x values like 1.149, that's in there. It's on the line somewhere. I don't know where exactly, and it's not really important because as soon as I struck that line in, I was able to answer this question for every value of x possible. And that's what makes sketching so useful, is you don't have to literally sit down and get your calculator out and knicker-knacker every single calculation. You can use a picture representation in order to get a rough idea of what the value of what sets of values make this fact true. So I have one more example to do for you, one that has a negative fraction, and then that'll wrap up this topic. So in this example, we're going to find all the places on a Cartesian plane where the y values are 6 less 2/3 for every step in x. So like all the other ones, we've got that value there to start from. So I'm going to find where y is 6. 1, 2, 3, 4, 5, 6, dash it in. And from that line, we're supposed to take away 2/3 of a box for every step we take in x. Now, that one's a fraction again. And like the last fraction one, not all of the x values are going to give you a clean number. So if you just think tactically, instead of using x is 1, x is 2, just skip straight to x is 3. Because if x is 3, 2/3 of x is 2. If you skip 4, skip 5, and go straight to 6, 2/3 of 6 is 4. So these are nice clean numbers that I can drop from my line. So 3, 6, 9 divides evenly by 3, so does 12, so does 15. 2/3 of 9 would be 6. 2/3 of 12 would be 8. 2/3 of 15 would be 10. Notice that these are going up by 3, and these are going up by 2. That's not an accident. That's how the pattern works. So if I start from 6 and I go over to where x is 3, that's here, I'm supposed to drop 2. So I do it. If I go to where x is 6, 1, 2, 3, 4, 5, 6, I'm supposed to drop 4 to there. So I'm dropping because it's a subtract. If I go to where x is 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, I'm supposed to drop 6. 1, 2, 3, 4, 5, 6 to there. And it looks like I'm off my grid. Notice that I'm dropping 2 over 3, dropping 2 over 3, dropping 2 over 3, right? It's not an accident. The same type of pattern is holding. So if I were to go back the other way, 3 steps in the x, 2 in the y, 3 in the x, 2 in the y, I can finish my line off the grid. And there you have it, a picture representation of every single xy pair where the y value follows this particular relationship.